Starting off, a few terms that are often used interchangeably in this work: AI, machine learning, and deep learning, and which can lead to some confusion. I just thought I'd spend a moment clarifying what these various terms mean, and there's probably some slightly different views on that, but I think this is the view that a lot of people will subscribe to, which is that at the top we have kind of an elusive goal of that we call artificial intelligence, which is a system that's capable of performing human-like tasks, a goal that we'll continue working towards probably many years and decades to come. Then getting a little bit more specific, we have machine learning, which is a particular approach to trying to achieve AI, and the characteristic of machine learning is that we're allowing our algorithms to learn from data, so they're not being explicitly programmed to carry out very specific steps of tasks. And then finally, we have deep learning as a subset of machine learning, which we have these machine learning algorithms learn directly from the raw high-dimensional data. And I'll expand a little bit on this on the next few slides. So here, just taking a moment to demystify machine learning, and I thought a good way to do that would be to take a look at a very, very simple machine learning model: straight line, a straight line with three parameters that we optimize to data. So although this is a highly simplified model, I think it serves to illustrate some of some more general concepts that you will encounter in working with machine learning. So one concept is three parameters of a model, which are optimized against some training data, shown here by the blue points, and optimized against some loss function. In this case, a chi-square. So we need some way of telling the model when it's doing well and when it's not doing well. Also, a very key concept is having test data. These are data that are being held out during the optimization of the model, but which are then used subsequently for testing how well the model is doing. Some of our test data may be in distribution, which just means it's kind of within the range where we had training data. This is where we expect our model to work well. Other test data may be outside the range or the domain where we had training data. In this case, things can work well, but they can also go poorly. And so it's important in assembling and compiling training sets for our machine learning models that we cover as many scenarios and as a broad of the data, a good range of that data domain as possible. And then we have a case here with a dashed line of a more sophisticated machine learning model that fits our data very nicely, but overfits, as we say. So it goes through all the 5 points, but then outside the range fails miserably. So making your model more sophisticated doesn't necessarily help you unless you also have more data and better data. So come back to this sort of mental picture. I find it helpful sometimes when things get really complicated in machine learning. Some of these, some of the concepts can be understood based on this very basic model. Now, moving to deep learning, as I mentioned, deep learning is a subset of machine learning, and in which the machine learning model on its own tries to learn relevant features from the raw data, which is this diagram tries to illustrate. So in a more classical machine learning approach, your raw data might be an image. That image is high dimensional. It may be thousands, tens of thousands of pixels. Through some algorithms, you try to extract some relevant features. Your feature extraction algorithm in this case could be detecting circles, which you would then associate with wheels, and that's what you would feed to your more conventional machine learning model. Would be how many wheels did we find in this image, how far are they apart, something like that. And then that classifier could learn to detect that as a vehicle. Whereas with deep learning, we're giving the full image to our machine learning model, and the machine learning model has to kind of figure that out by itself. So a more data hungry approach, but also potentially a more flexible approach. Taking a closer look at deep neural networks. The deep neural network is a network with many layers, each layer consisting of units that we call neurons. Neurons perform linear operations on input data. So a single neuron would be your linear model from my first slide. But then as you put them together through nonlinear activation functions, what you get is a machine learning algorithm that can perform a highly nonlinear operation of input data. And these are the type of networks that have been particularly successful, especially in image analysis tasks. And the type of deep learning network that you will often hear referred to is a convolutional neural network, or CNN for short. And these are a special category of deep neural nets that utilize something called convolutional filter, which is over here. It's a kernel that moves across your image, and the same weights move across that image, and then some type of simple operation is applied to that little collection of pixels. You may pick the maximum value or the average value of those pixels, and then that propagates through the network. And although to some degree these machine learning models have a character of black boxes, we don't know fully what they do to arrive at their decisions. It's not completely impossible to look inside them and gain some insights into how they make their decisions, which is what's illustrated on the left there. Now, oh dear, okay, I probably should have tested this. I think we may have to come back to this at a later time. No, it's okay. I think we'll skip this. I'll just jump back. Let's see if I can get back to the present review. Is that here? No. Kind of. All right. Sorry about that. I should have made an effort to test this ahead of time. This is why I usually don't have video nor audio in my presentations. You were supposed to see what I wanted to illustrate here was just how far advanced things are in computer vision. As you can maybe figure out from the text there. What I was going to show you here was a cute little video of my nephew, and then with processed by a pre-trained, off-the-shelf, open source object detection model, something that I can go and grab online, and with a few lines of code, I can run this deep neural network on a piece of on a video segment, and it can detect objects in that video. And so, having never met my nephew before, this object detection network recognizes him as a person throughout most of that little video, although towards the end, as he falls to the ground, it thinks he's a doll. But that was the way to answer. But my main point here was just that in computer vision, where training data is so abundant, it's really amazing how far that has advanced to kind of a production level. And so I think that's something we could aim for in acoustics as well, as to aim for something like that. Now, oops. Moving on, this is just really about my own work. So this will be really brief. Just another example of where computer vision is used. Recently, I started a new job with this company, Ocean Robotics, that's based out here west, unmanned vessels that have cameras, thermal and optical, mounted on them. And so that's another place where machine learning goes in and tries to automate the analysis of video imagery, turning an unmanned surface vessel into an autonomous surface vessel. So it's But I'm here today to talk about acoustics. So I'll bring us back to acoustics right away. So the common approach that we've seen adopted repeatedly in the last few years with deep learning applied to acoustics is to take all of these tools and tricks that's been developed for computer vision and then apply them to spectrograms. And this is not the only way of doing deep learning with acoustics, but it's certainly the one that's been pursued the most, and certainly the one that's that has been that's come the furthest, I'd say. And so the pipeline that I think we've seen a couple of times already consists in transforming a waveform to a spectrogram, feeding that to a CNN, a convolutional neural network, which then outputs a list of scores for the various labels. And that can be then threshold to produce a detector. One key limitation, in my opinion, of this approach is limited temporal memory that only goes as far back as the duration of your spectrogram, which you can only make so long, owing to primarily to computational limitations. Still, there's a lot of potential here, and there's a lot of untapped potential. So it's worthwhile to continue working with this approach still. And it does work very well. I don't know if any of you are familiar with some of these apps, but where training data is abundant, you can get these types of models to recognize sounds quite well. Moving to the underwater domain, things get a little bit more challenging. I think we're often confronted with situations in which signal to noise ratio is quite poor. We have quite substantial propagation effects, as we've heard about already earlier today. Training sets are just not as large. And then sometimes we also need these models kind of a separate challenge, but we need them to run on smaller devices that are power limited, say, during long-term deployment. So this all adds to the difficulty of doing this in the ocean. Nevertheless, as I mentioned, there has been a lot of pilot studies, proof of concepts that are now maturing into operational tools. I think the North Atlantic right whale detector is an excellent example of that. So there's plenty of proof that this works, and we just gotta keep working at it. Coming back to the propagation effects, so this is a real challenge, and I love this example that I have from Jasper Keynes at ONC to illustrate this. Propagation effects can really alter these calls that we're trying to detect. This is the case of the same call, but detected at two different locations, two different ONC cataphone nodes, in which, as you see, there's a lower component that entirely disappears in one place. So imagine that you've trained your network only on data from one location and you're testing it out in the other. What is it going to classify? What is it going to detect? So in assembling these training sets, we really need to derive data from as many possible acoustic environments as we can. And we need to come up with ways in which we can easily adapt models to new environments. Because if we have to collect thousands or tens of thousands of examples from every new environment we're deploying in, then we're not really creating a tool that's particularly useful. And this is where transfer learning comes into the picture, an approach to taking a deep learning model that's already been trained on a very large data set and then repurposing it to do something a little bit different, maybe solving the same task in a different environment or a slightly different task, but still related task. And with this type of approach, if you start with a really small model, you can adapt this model through using a much smaller number of annotated samples. And this is something the Meridian team has been pursuing lately at Dalhousie University, working specifically with the North Atlantic right whale upcall and trying to repurpose or adapt deep learning acoustic detector that was trained on a data set from one location to a different location. and seeing how that how that works out as a function of how many training samples you have available in your location, and getting promising results there. Another neat sort of tool in the deep learning toolbox are various tools for generating new training data. When there is a lack of training data, you can augment data in various ways. One concept that's quite neat is that of style transfer. To the left is style transfer applied to imagery, in which you take a photo or a painting, and then you kind of preserve the semantic information of that painting, but you render it in a different style in a somewhat controlled manner. And to the right is another little video clip that I'm not going to be able to show or play for you, but essentially the same concept, but done with audio. So taking a short piece of music played on a piano and then transforming it to what would this sound like on a violin or something. So, you know, those are still not tools that we've really started using in the context of underwater acoustics, but it's something that we could start playing with in the future. Now, since I'm running short on time, just to show that there's so much I didn't talk about in this talk. We'll come back to that another day. But one thing to emphasize is that this spectrogram approach is certainly not the only approach to deep learning in underwater acoustics. There are other time domain models that are relevant to look at as well. My thoughts on the path forward: we need to become even better at sharing data and train models, and this is gradually happening. And also, we need the tools to support all of this, both for the model developers and the people who are going to use these trained models. And all of this is happening too. And I've just thrown in a few a bit of advertisement for the work that the Meridian team is doing, but others are doing work in this area as well. One quick comment about annotations. This is, something that in the context of the Hello project we are working with a lot, is to compile and aggregate annotations of acoustic, which is really, without this, it's very hard to do much machine learning. And we've come to realize just how challenging that is, keeping track of all the aspects of the metadata. And there's so much information surrounding how the annotations were made that are important for a machine learning developer to make correct use of the annotations. It's important to know if every sound in this file was annotated or just some of them, etc. And I'm not going to have time to dwell at that now, but I do want to highlight just that there is a really nice paper by Marie Rolf that goes into this at a much more detailed level, and there's a lot of good insights there for anyone managing metadata and annotations included on how that all the information you need to capture. And finally, some useful resources that I think I'll just leave there, and hopefully we'll make the slides available after the workshop, and people will be able to go find these links. Yeah. Okay, I'll end it there. I think we can do questions if there are any.